Hello, my name is Suhail Singh. I'm a second year aerospace engineering major, and today we will be talking about combustion dynamics in a rocket tube. Now, you all may want to know, why should we care? Well, what we will see during this lab in the rocket tube is exactly what happens in a pulse jet engine, which, as the name implies, works by injecting fuel into the combustion chamber in pulses rather than in one stream. These type of combustors are more efficient than steady combustors and have increased combustion intensity. A rocket tube is essentially a long tube with a source of heat placed inside of it. That heat source creates a convection current which in certain ranges of positions creates an oscillating pressure wave that causes the tube to resonate in frequencies that the human ear can perceive. In this experiment we will be using pressure sensors to find the frequency and the amplitude of the resultant pressure wave, and we'll be able to model the pressure wave for this rocket tube. In this experiment, we are mainly concerned with measuring two things: the pressure and the reaction rate. We measure the pressure at three different locations on the rocket tube using piezoelectric transducers, which creates a small current when a force is applied to the sensor. The sensors were positioned 18 inches apart from one another, one at the center of the tube, one 1/4 of the way from the top of the tube, and the other 1/4 of the way from the bottom of the tube. We can measure the reaction rate using a photomultiplier and a filter, so only photons that are produced in the burning of the fuel, in this case propane, are captured. In this experiment, we took measurements under four conditions. Our first run, we put the flame at the 0 position and kept the valve open so that there would be no oscillations. Run 2 had us close the valve, which forced the flow to go up through the rocket tube, creating resonance. Run 3 had us raise the flame 2 inches, and run 4 had us raise the flame until the oscillation stopped, which was about 6 inches. Now we have collected data from both the piezoelectric transducers and the photomultiplier. However, the data from the piezoelectric transducers is given in voltages rather than what we need in pressure. So, in order to convert from one to the other, we use this calibration curve, which shows a linear relationship between pressure and voltage, which makes it fairly easy to convert from one to the other, as shown here in this equation. From those pressure values, we want to relate them to something that you and I can understand, which in this case would be human hearing, which is why we'd convert from pressure to decibels using this formula, where P threshold is the pressure threshold of human hearing. From that, we arrive at these graphs showing us the peak decibel number and frequency for each of the pressure sensors. I am going to quickly go through these graphs for each run. In order to relate between theoretical and experimental, you also want to find the resonant frequency of the rocket tube. As with all sound-emitting tubes, the wavelength of the sound emitted by the rocket tube is equal to 2 times the length of the tube itself. A in this equation is the speed of sound for air at room temperature, which is about 343 meters per second. The rocket tube used in this experiment is 72 inches long, so the resonant frequency is about 93.8 Hz. We should expect the pressure waves to have a frequency similar to this resonant frequency. Using the graphs, we were able to find the peak frequencies for each pressure sensor and of the photomultiplier for each run. As shown here, when resonance occurs, the frequency of the pressure wave and of the flame is 97 Hz, which is fairly close to the resonant frequency of 93.83 Hz. We also see a big discrepancy between runs 2 and 3 for the peak frequencies of the photomultiplier, but this has more to do with the fact that we move the flame without moving the photomultiplier. If we had kept the photomultiplier and the flame level with each other, the peak frequency for run 3 would have almost certainly been 97 Hz. From those graphs we also got the values for the max sound level for each run of the experiment for each sensor. As shown here, runs 2 and 3 have very similar sound levels, and rounds 1 and 4 also have very similar sound levels, mostly due to the fact that runs 2 and 3 had a resonance and runs 1 and 4 didn't. The relative phase angle tells us where in the wave function the upper and lower sensors are compared to the middle sensor. As shown here, again, runs 2 and 3 are similar, and runs 1 and 4 are also similar. Now let's discuss these supplemental questions. In this question, we have pretty much replaced our current interference filter with a new one that filters light between 415 and 450 nanometers. This would not work with our experiment, as propane burns at a range of between 306 and 311 nanometers, meaning that we would not actually get enough data in order for this to work. However, if we use hydrogen gas instead of propane, we can actually use this interference filter because hydrogen does burn within the spectrum. This question asks how we can change the resonant frequency of the Ricot tube, and the only way we can do that is either change the gas, change the temperature, or change the length. We don't have much control over the gas, so we can only change the ambient temperature or the length of the Ricot tube. I wanted for a minute to discuss the pressure oscillations within the Ricot tube. I went and graphed the pressure function for runs 1 and 2. As you can see, there's a huge difference between the pressure function when there's harmonic resonance and when there is no harmonic resonance. This acoustic pressure ends up balancing itself when it's resonating, making the entire system more stable. Thank you for listening to my presentation.